So here we are back from Thanksgiving. I hope you enjoyed your break. I'm going to get looking at, we're about to start chapter 10, but really quickly, I'm going to review over chapter 3. What we learned about in chapter 3 was called exponential and logarithmic functions, if you remember. That's what we talked about in chapter 3. So this first, really, questions 1 and 2 derived from this paragraph right here. So it says, 2 ant colonies are growing at the exact same rate. The first colony, however, has a larger population than the second colony. The equation f of t equals 300 times 1.03 to the power of t illustrates the population of the first colony. So this is exponential because the variable is in the power. Just a reminder, since it's been a week since we've done anything, exponential has a base raised to a power. That's exponential here. So this is the first colony. What equation represents the second colony if G is 85% the size of F? And so we have to remember, when you come off this, what is the initial population? And what we've learned, if you use like the formula chart or anything like that from Google Classroom, we'll go to the formula chart, and I'll also add a tab and show you from Power School Learning what that would look like. So from Google Classroom, if I click the formula chart, just as a reminder for exponential, your initial is that P. That P stands for principal. The initial is the front amount. In front of, this is the base raised to a power, or here the base is E raised to the power of RT. The P is the initial amount. If you were using Power School Learning, let me show you how you get to the formula chart. From the front page of the classroom, you can go under digital resources here and click there for the formula chart. Or if you're in chapter 10, the formula chart on the digital resources, it's listed, it's the second link for 10.1. So anyways, you might want that formula chart open. I'll just leave it open right here. So the initial amount here is 300. This is the initial population. That right there is the population. So the 1.03, that is the growth rate. So it says 2 ant colonies are growing at the exact same rate. The first colony, however, has a larger population. So this is the population. Then the second colony. The equation here illustrates the population of the first colony. The growing at the exact same rate, that's referring to this portion of it right there. That's the growth rate. And we know it's growth because it's greater than 1. If it was less than 1, it would be a decay rate. But since it's greater than 1, it's growing. So population is 300, growth rate is 1.03. Okay, so we read the first question. What equation represents the colony if G is 85% of the size of F? So what is that changing? The population or the growth rate? What changes for number 1? Population. And so you need to take 85% of 300. So 85% of 300 is what we would have to find, which 85%, if you remember, the way to get rid of percent is you divide it by 100%. Now, what happens is these percent symbols cancel out, and you find out that is 0.85. So really the math you do is 0.85. Mathematically, of means times 300. That right there will give us our population. So I'll go 0.85 times 300. The population of G is 255. That's the population. So if we had to write an equation, I want to go back to this. 2 ant colonies are growing at the exact same rate. What does that mean if it's the exact same rate? Exact same. And so G's equation would look something like this. It would be G of T would equal, we found out the population is 255. 255 times 1.03 to the power of T. So the rate stayed the same. What changed was the population. And number 2 says, draw a first quadrant sketch modeling the populations of F and G over time. And what I know, without even going to the graph, I'm just going to add a little graph here. is that the initial populations is where the graphs will start. Since we said they are growing, that means they're going to increase. So one will start at 300 and go up. The other will start at 255 and go up at the same speed. So on this equation, like that would be G, this would be F. And just as a reminder, F would start at 300 and G will start at 255. So that's what they're going to look like when we graph them, is they're both going to be growing. If you remember, exponentials look like an airplane taking off. And so these would be like an airplane taking off to fly, one starting at 300 and the other starting at 255. So let's go to Desmos and graph these. The equation they gave us, that we did not have to do any work on, was 300 to the 1.03 power of t. So I typed that in just as it looks, and Desmos does handle t's just like x's. So you can use a t in Desmos just like you would an x, and it'll graph it just the same. It'll put t as the x-axis. And we're saying g is 255 to the 1.03 power of t. To make this look right, I'm going to go over here to my settings, and I'm going to change it. I know it's going to start on the y-axis at 300. This one at 300, this one at 255. So for that reason, I'm going to pick a bigger number. I'm just going to say like 500. And so you see that there. And since I want only the first quadrant, I can just slide it to the right. And you can see these are growing at the same rate. It's just this one happens to start at 300. This one starts at 255. Okay, so that's what it would look like first quadrant wise. And t would be the amount of time that goes on. Any questions over the bell ringer there?